What if the greatest breakthroughs in space technology weren't born in modern labs, but in the minds of astronomers long forgotten? Picture this: centuries ago, thinkers gazed at the stars with nothing but their eyes and imagination, sketching theories so bold they were laughed at or ignored. Yet today, their wildest ideas are the very foundation of how we explore the cosmos. It's a story of brilliance lost and found where the past and future collide in ways that will leave you awestruck. Think about the last time you looked up at the night sky. The same stars that captivated ancient astronomers now guide our satellites and rovers. But here's the twist: those early stargazers didn't just observe, they predicted. They dreamed of propulsion systems without fuel, of telescopes that could peer beyond our galaxy, even of civilizations on distant worlds. At the time, it sounded like fantasy. But fast forward to today, and their visions are alive in ion drives, gravitational wave detectors, and the search for extraterrestrial life. How did they know? How did these forgotten theories, buried in dusty manuscripts or dismissed as heresy, become the blueprint for our space age? This isn't just a history lesson, it's a revelation. When we uncover these hidden connections, we're not just honoring the past, we're unlocking the future. Because every time we revisit these old ideas with fresh eyes, we find new clues for tomorrow's discoveries. Maybe the next leap in space travel is already waiting in some overlooked notebook or crumbling star chart. So let's embark on a journey through time, where the dreams of the past light the way to the cosmos of tomorrow. By the end, you'll see the night sky and the genius of those who studied it in a whole new light. Johannes Kepler wasn't just staring at planetary motions, he was sketching cosmic highways. In the early 1600s, while most believed the heavens were fixed and unchanging, this mathematician dared to imagine ships sailing between worlds. His notes, scribbled between calculations on orbital mechanics, described crews enduring weightlessness and navigating celestial currents. At the time, it seemed like fiction. Yet today, his laws of planetary motion guide every satellite trajectory, and his vision of crewed spacecraft mirrors our missions to the International Space Station. Then there's Konstantin Tsiolkovsky, a near-deaf schoolteacher in rural Russia who transformed rocketry from fantasy to physics. In the late 1800s, while others scoffed at space travel, he penned equations proving multi-stage rockets could escape Earth's gravity. His blueprints for liquid fuel engines and orbital habitats were ridiculed until they became the foundation for NASA Apollo program and SpaceX's reusable boosters. Tsiolkovsky's most haunting prediction, his famous line, "Earth is the cradle of humanity, but one cannot live in a cradle forever." These weren't isolated geniuses. Centuries earlier, Islamic astronomers like Alhazen built camera obscuras to study light, unknowingly laying groundwork for modern telescope optics. In China, Zhang Heng's seismoscope detected distant quakes with eerie precision, hinting at technologies we'd later use to monitor planetary tremors on Mars. What united them? A refusal to accept limits. They worked with quills by candlelight without computers or satellites, yet their ideas outran their eras. Consider the backlash they faced. Kepler's own mother was accused of witchcraft amid his celestial theories. Tsiolkovsky was labeled a madman for suggesting metal could fly. Their stories reveal a pattern. Revolutionary ideas often arrive wrapped in ridicule. Yet history vindicates the bold. When we examine their original manuscripts filled with marginalia, corrections, and bursts of insight, we're not just reading notes. We're witnessing the moment humanity first reached for the stars. Johannes Kepler's obsession with cosmic harmony began with a mystery. Why didn't the planets move in the perfect circles everyone expected? For centuries, astronomers clung to the idea of divine symmetry, convinced celestial orbits had to be flawless. But Kepler, armed with meticulous notes from his mentor Tycho Brahe, saw something different. The numbers didn't lie. Mars's path was slightly stretched, an oval rather than a circle. In 1609, he shattered tradition with his first law: planets orbit the sun in ellipses. At the time, it was heresy. Today, it's the reason your GPS doesn't send you driving into a lake. Here's the magic of Kepler's second law: planets speed up as they near the sun and slow down farther away. It's why comets like Halley's dart passed us in a blaze, then vanish for decades. Modern spacecraft use this same principle, called orbital mechanics, to slingshot around planets. When NASA Voyager probes toured the solar system, they weren't just following a map. They were dancing to Kepler's 400-year-old rhythm, using gravitational assists to gain speed without fuel. Even SpaceX's Falcon rockets rely on these laws to deploy Starlink satellites with pinpoint accuracy. Then there's the third law, the hidden equation that ties a planet's orbit to its distance from the sun. It's the reason we can calculate how long a trip to Pluto will take or predict when a distant exoplanet might pass in front of its star. Kepler called this celestial choreography the music of the spheres, a symphony only mathematics could hear. Little did he know, his sheet music would one day guide rovers across Martian dunes and landers on icy moons. The real shock: Kepler almost missed it. His early sketches included bizarre geometric shapes, nested cubes and spheres, as he struggled to force the data into ancient Greek ideals. It wasn't until he abandoned 2,000 years of dogma that the truth emerged. That's the lesson here. Sometimes the universe's greatest secrets hide in the imperfections, the wobbles, the outliers, and the boldest ideas, the ones that rewrite the rules, often start as whispers against the roar of convention. Isaac Newton once asked a simple question: what if you could throw something so fast it never hit the ground? Picture this: atop a towering mountain, a cannon fires a projectile horizontally. With each shot, the cannonball flies farther before curving down to Earth. But Newton imagined one final shot where the ball moves so swiftly that Earth's curvature drops away beneath it at the same rate the ball falls. The result: a perpetual loop around the planet. In 1687, this was just a chalkboard fantasy. Yet 3 centuries later, his so-called Cannonball thought experiment became the operating manual for every satellite humming overhead. The brilliance wasn't just in the idea, it was in the math. Newton realized orbital motion was a tug of war between velocity and gravity. Too slow and the object crashes. Too fast and it escapes into space, but hit that perfect middle ground and you achieve what engineers now call circular orbit velocity, about 17,500 miles per hour for Earth. That precise calculation is why your phone's GPS doesn't send you into a cornfield, and why meteorologists can track hurricanes days in advance. Here's what's wild: Newton had no rockets, no computers, not even a telescope powerful enough to see Jupiter's moons clearly. He worked this out using quill and parchment, armed only with his laws of motion and universal gravitation. Today, those same equations determine everything from the altitude of SpaceX's Starlink satellites to the re-entry angle of the International Space Station. When a Falcon 9 booster lands itself on a drone ship, it's not just cutting-edge tech, it's Newton's 300-year-old physics in action. But the real kicker: Newton's sketch didn't stop at Earth. In his notes, he mused about cannons on the moon, even speculating about objects orbiting the sun. That audacious leap from earthly artillery to cosmic trajectories laid the groundwork for humanity's greatest achievements. The Voyager probe sailing beyond our solar system, Newton's math, the James Webb Space Telescope holding steady at Lagrange point 2, Newton's math. Every time a mission control room erupts in cheers at a successful orbital insertion, they're celebrating a 17th century genius who saw the future in a falling apple and a hypothetical cannonball. What makes this story unforgettable isn't just the prediction, it's the resistance. For decades, Newton's peers dismissed orbital mechanics as useless abstraction. Who needed theories about objects that couldn't possibly exist? Yet history has a way of humbling skeptics. The same principles once deemed impractical now form the backbone of our digital world, from satellite TV to global banking systems. It's a reminder that today's impossible might be tomorrow's instruction manual, and that the most revolutionary ideas often begin as quiet thoughts scribbled in the margins. Konstantin Tsiolkovsky sat in his remote Russian workshop, deaf to the laughter of critics but tuned perfectly to the music of the cosmos. While the world dismissed space travel as pure fantasy, this self-taught physicist scribbled equations that would one day launch humanity beyond Earth. His breakthrough came in 1897 with what we now call the Tsiolkovsky rocket equation, a deceptively simple formula that cracked the code of cosmic escape. At its heart was a brutal truth: to reach orbit, you don't just need fuel. You need exponentially more fuel to carry that fuel. The equation looks like this. The change in a rocket's velocity equals its exhaust speed multiplied by the natural logarithm of its starting mass divided by its final mass. Translation: every ounce of payload requires staggering amounts of propellant. For a Saturn V rocket to lift 3 astronauts toward the moon, it had to burn through 2,000 tons of kerosene and liquid oxygen in just 2.5 minutes. Tsiolkovsky proved this mathematically, no trial and error, just pure physics on paper, half a century before the first V2 rocket left the atmosphere. Here's where it gets visionary. Tsiolkovsky didn't stop at single-use rockets. His notebooks detailed multi-stage designs where empty fuel tanks would detach mid-flight, shedding dead weight to boost efficiency. Sound familiar? That's exactly how SpaceX's Falcon 9 drops its first stage back to Earth for reuse. Even more astounding, he calculated the exact speed needed to break free of Earth's gravity, approximately 25,000 miles per hour. That number became the gold standard for every crewed mission from Mercury to Artemis. But the real genius was in his foresight. While others imagined rockets as futuristic trains or airships, Tsiolkovsky saw them as precision instruments governed by immutable laws. He predicted liquid hydrogen as the ultimate fuel decades before it powered the space shuttle's main engines. He sketched space stations with rotating wheels for artificial gravity blueprints that inspired the International Space Station's design. And perhaps most poignant, he wrote detailed plans for interplanetary travel, including life support systems and closed ecosystems, at a time when airplanes were still novelties. The cruel irony: Tsiolkovsky never saw his theories take flight. He died in 1935, 12 years before the first artificial satellite reached space. Yet his equation lives on every launch pad, in every mission control room, and in every spacecraft threading its way between planets. When Elon Musk tweets about the tyranny of the rocket equation, he's wrestling with the same limitations Tsiolkovsky quantified over a century ago. That's the power of a single idea born in isolation, ridiculed in its time, but destined to become the silent partner in humanity's greatest adventures. Einstein scribbled his theory of relativity in 1905 while working as a patent clerk, calling it a happy thought that would upend physics. At the time, even fellow scientists struggled to grasp its implications. How could time slow down for a moving clock? Why would gravity bend light itself? These weren't just abstract puzzles. They were glimpses into a universe far stranger than anyone imagined. Fast forward to today, and those same equations are the unsung heroes behind every Uber ride, every food delivery app, every hiker rescued thanks to a phone's blinking blue dot. Here's the paradox Einstein uncovered. Time isn't absolute. The faster you move, the slower your clock ticks compared to someone standing still, an effect called time dilation. Even more bizarre, gravity warps time too. Clocks at higher altitudes, where Earth's pull is weaker, actually tick faster than those at sea level. To your phone's GPS receiver, these differences aren't theoretical quirks, they're make-or-break calculations. Satellite atomic clocks orbiting 12,000 miles up experience both effects. They move at nearly 9,000 miles per hour, speeding time up slightly, while being farther from Earth's gravity, slowing time down more. The net result, those clocks gain about 38 microseconds daily. That might sound negligible until you do the math. Light travels nearly 7 miles in 38 microseconds. Without relativity's corrections, GPS locations would drift by over 6 miles per day. Your turn left in 500 feet prompt would send you into a lake by week's end. That's why engineers bake Einstein's equations directly into the system, tweaking satellite clocks to compensate for spacetime's wrinkles. The same theory, once deemed too abstract for practical use, now quietly orchestrates global shipping routes, emergency responses, and even dating app meetups. Einstein's genius wasn't just in predicting these effects, it was in how he discovered them. He conducted thought experiments, imagining chasing light beams or falling in elevators. No labs, no equipment, just pure mental modeling. Today, those exercises seem almost prophetic. When Lockheed Martin engineers adjust satellite software for relativistic effects, they're essentially debugging reality using a patent clerk's daydreams. The ultimate irony, Einstein doubted space travel would ever be possible, yet his work became the bedrock of orbital navigation. The lesson here transcends physics. Some ideas are so radical they take decades or centuries to find their purpose. What seems like ivory tower speculation today might be tomorrow's indispensable tool. Right now, quantum theorists are grappling with concepts just as bewildering as relativity once was. If history's any guide, their equations could one day power technologies we can't yet fathom. So the next time your map app guides you flawlessly through an unfamiliar city, remember, you're not just seeing satellites at work. You're witnessing a century-old thought experiment playing out in real time, proving once again that the universe rewards those who dare to imagine its deepest secrets. Heinrich Olbers stared at the night sky in 1823 and asked a question that seemed absurd. Why is space so dark? If the universe is infinite and filled with stars, shouldn't every line of sight eventually hit a blazing sun? The night should glow like daylight, yet it doesn't. This simple observation, now called Olbers Paradox, didn't just puzzle astronomers, it cracked open the door to modern cosmology. At the time, most scientists assumed the universe was static and eternal. But Olbers' math revealed a glaring inconsistency. Imagine standing in an endless forest where every gap between trees leads to another tree. No matter where you look, your view would end at a trunk. Apply that to stars, and the entire sky should be a solid sheet of starlight, yet it's not. Olbers proposed patches of cosmic dust might block the light, but that didn't hold up over time. Dust would heat up and glow just as brightly. The real answer, hidden for a century, would rewrite humanity's place in the cosmos. Enter Edwin Hubble in the 1920s, peering through the Mount Wilson telescope. he noticed something bizarre. Distant galaxies weren't just sitting in space. Their light stretched toward the red end of the spectrum, a telltale sign they were racing away from us. The farther the galaxy, the faster it receded. This wasn't just motion, it was evidence the universe itself was expanding, like dots on an inflating balloon. Suddenly, Olbers Paradox made sense. If space stretches, starlight loses energy over vast distances, shifting into invisible infrared or fading entirely. The night stays dark because the universe has a finite age, about 13.8 billion years, meaning light from the most distant stars hasn't reached us yet. But Hubble's discovery did more than solve an old riddle. It gave birth to the Big Bang theory. Those fleeing galaxies imply everything was once compressed into an unimaginably dense point. Run the cosmic film backward, and you reach a moment of creation, a singularity where time, space, and energy erupted into existence. Olbers couldn't have known his question about darkness would lead to this revelation. Yet his paradox became the first thread in a tapestry that now includes cosmic microwave background radiation, dark energy, and the accelerating expansion of everything. Here's the beautiful irony. Olbers assumed an unchanging universe because that's all his era could conceive. Today, we know the cosmos is dynamic, expanding, evolving, with galaxies born and dying. That darkness he puzzled over, it's the echo of beginnings, the shadow cast by creation itself. Every time you look up at a starry sky and marvel at the black between the lights, you're witnessing the evidence of a universe with a story, one that began in fire and unfolds in mystery. The answer wasn't in the stars Olbers saw, but in the darkness he couldn't explain. And that's how science often works, not by finding what we expect, but by stumbling into the questions we never thought to ask. In the 1700s, two mathematicians, Leonhard Euler and Joseph Louis Lagrange, solved a celestial puzzle that seemed more like poetry than physics. They imagined points in space where gravitational pulls from massive objects like the Sun and Earth would perfectly balance, creating cosmic eddies where smaller objects could hover effortlessly. At the time, these Lagrange points were just elegant solutions to abstract equations. Today, they're the most coveted parking spots in the solar system. Take the James Webb Space Telescope, humanity's most powerful eye on the cosmos. It doesn't orbit Earth or the Sun in the usual sense. Instead, it's stationed 1,000,000 miles away at Lagrange Point 2, or L2, a gravitational sweet spot where Earth and the Sun's tugs cancel out just enough to let the telescope hold steady with minimal fuel. From this vantage, Webb's sunshield blocks both stellar glare and Earth's heat, giving it an unobstructed view of the universe's faintest whispers. But L2 isn't just a lonely outpost. It's part of a 5-point celestial highway system. Points L1 and L3 lie along the Earth-Sun line, perfect for solar observatories like the Deep Space Climate Observatory, which monitors space weather that could knock out power grids. L4 and L5, however, are the real marvels. They form stable triangular zones with Earth and the Sun, where objects can linger for eons. Astronomers have found Trojan asteroids trapped there, and future missions might use these regions as interplanetary depots, storing fuel or supplies for journeys to Mars and beyond. Here's what Euler and Lagrange couldn't have foreseen. Their math now shapes interstellar strategy. When China's Chang missions explored the Moon, they used a quasi-halo orbit around L2 to relay data back to Earth. NASA's upcoming Artemis Gateway, a lunar space station, will orbit near L1 to serve as a jumping-off point for astronauts. Even private companies eye these points. SpaceX once proposed a Starlink constellation at L1 to blanket the globe in internet coverage. The genius of Lagrange points lies in their economy. In space travel, fuel is everything. A satellite parked at L2 can stay in position for years with tiny adjustments, while a traditional orbit might demand constant corrections. That efficiency is why missions like Euclid, Europe's Dark Matter Hunter, and First NASA Exoplanet Tracker all queue up for these slots. They are the ultimate rest stops in the void where the universe itself handles the parking. What's astonishing isn't just the prediction, it's the persistence of the vision. Euler and Lagrange worked with quills and parchment, sketching curves they'd never see realized. Yet their calculations now guide billion-dollar telescopes and interplanetary ambitions. As we plan missions to Venus's L1 or Jupiter's Trojans, we're not just exploring space. We're fulfilling an 18th-century dream, one where mathematics revealed hiding places in the sky, waiting patiently for humanity to arrive. Robert Bussard stared at the cosmos in 1960 and saw something everyone else missed, an endless fuel supply hiding in plain sight. While NASA was still perfecting chemical rockets, this visionary physicist imagined spacecraft that could drink from the galaxy itself, scooping up stray hydrogen atoms between stars to power nuclear fusion engines. Critics called it science fiction. Today, engineers are racing to turn his Bussard Ramjet concept into humanity's ticket to interstellar travel. Here's how it works. In the vacuum of space, hydrogen gas floats at about 1 atom per cubic centimeter, seemingly nothing. But a spacecraft moving at even 10% light speed would encounter these particles like a car plowing through rain. Bussard proposed using enormous electromagnetic fields, stretching hundreds of miles wide like invisible nets, to funnel this hydrogen into a fusion reactor. The result, a self-sustaining engine needing no onboard fuel, accelerating continuously as it harvests interstellar material. The faster it goes, the more hydrogen it collects, creating an exponential speed boost limited only by relativity. What seemed impossible in the 60s now looks increasingly plausible. Modern studies show magnetic scoops could be made from superconducting coils thinner than spider silk, deployed in vast mesh formations. NASA's Innovative Advanced Concepts Program funds prototypes of fusion-driven ramjets for Mars missions, while private ventures like Breakthrough Starshot explore scaled-down versions for probes to Alpha Centauri. Even more remarkably, astronomers have identified hydrogen highways, regions where interstellar gas concentrates, offering potential fueling routes for future starships. The hurdles remain staggering. At high velocities, hydrogen impacts would create deadly radiation, requiring advances in shielding. The reactor itself would need temperatures exceeding 100 million degrees to fuse collected atoms, far beyond current tokamak designs. Yet recent breakthroughs in inertial confinement, fusion, and plasma containment suggest solutions may be closer than we think. When China's East reactor sustained fusion for 17 minutes, or when the National Ignition Facility achieved net energy gain, they weren't just making headlines, they were accidentally proving pieces of Bussard's puzzle. What makes the ramjet idea endure isn't just its elegance, but its inevitability. Chemical rockets could never reach another star. They'd need more fuel than exists on Earth. Antimatter propulsion requires manufacturing quantities we can't produce. The ramjet offers the only known method where the journey itself provides the means. That's why scientists now speculate about slow boats, generation ships traveling at mere fractions of light speed, their crews sustained by fusion-powered ecosystems, arriving centuries later in systems we've only glimpsed through telescopes. Bussard never lived to see his engine built. He died in 2007, decades before his ideas entered mainstream aerospace research. But his legacy lives on every time a physicist tweaks a plasma containment model or an engineer tests a new superconducting magnet. The galaxy's hydrogen still drifts unseen and untapped, waiting for the day when some distant descendant of Apollo looks up from their controls and realizes they're not burning fuel. They're sailing on star stuff itself, riding a current first imagined by a dreamer with a slide rule and the courage to think big. Fritz Zwicky peered through the telescope at California's Mount Wilson Observatory in 1933 and saw something that shouldn't exist. The Coma Cluster, a sprawling group of galaxies, was spinning so fast its visible stars should have torn apart, flung into the void like marbles from a slingshot. Yet there they were, held together by some invisible glue. Zwicky didn't hesitate. He called it Dunkel Materie, a dark matter, and declared it made up most of the universe's mass. The scientific community laughed. How could something we can't see or touch dominate the cosmos? Decades later, we know Zwicky was right. But here's the twist. His discovery wasn't just about finding missing mass. It rewrote the rules of reality itself. When astronomer Vera Rubin studied galaxy rotations in the 1970s, she found the same anomaly. Stars at the edges of spiral galaxies moved just as fast as those near the center, defying Newton's laws. The only explanation, an enormous halo of invisible matter, bending space like a hidden hand. Today, dark matter accounts for 85% of the universe's mass, shaping everything from galactic collisions to the cosmic web that threads the void. Zwicky's story is a masterclass in scientific rebellion. While others dismissed his work as numerology, he doubled down, cataloging supernova and even predicting gravitational lenses before Einstein's equations were tested. His methods were unorthodox. He once called colleagues spherical bastards, because they were bastards no matter which way you looked at them, but his intuition was razor sharp. The same man who coined dark matter also envisioned neutron stars and jet engines for spacecraft, ideas decades ahead of their time. What's haunting is how close we came to ignoring him. Dark matter doesn't emit, absorb, or reflect light. It doesn't interact with ordinary matter except through gravity. For all intents and purposes, it's a ghost. Yet without it, galaxies wouldn't form, and the universe would look utterly different. Modern detectors like the Large Hadron Collider and experiments in abandoned gold mines hunt for dark matter particles, but they remain elusive. Some theories suggest actions or WIMP, weakly interacting massive particles, while others propose modifications to gravity itself. The irony, Zwicky's Dunkel Materie might be just the beginning. Recent studies of galactic collisions show dark matter behaving in ways no model predicts, clumping unexpectedly or lagging behind visible matter. Could there be multiple types? Is it a shadow universe parallel to ours? Every time we think we've pinned it down, it slips away, leaving more questions. Zwicky died in 1974, never seeing his vindication. But his legacy lives on in every telescope trained on gravitational lenses, every supercomputer simulating cosmic evolution. The universe, it turns out, isn't just what we see. It's what we can't. A lesson whispered by an outcast astronomer who dared to trust the invisible over the obvious. And that's the beauty of science. Sometimes, the most outrageous ideas are the ones holding reality together. Robert Goddard lay in a Massachusetts field in 1926, watching his creation, a 10-foot-tall metal contraption, lift off with a roar. For just 2.5 seconds, the world's first liquid-fueled rocket climbed 41 feet before crashing into a frozen cabbage patch. Newspapers mocked it as moon rocket fizzles, and physicists dismissed Goddard as a fantasist. Yet hidden in that brief, wobbly flight were the seeds of every modern rocket from the Saturn V to SpaceX's Starship. What made Goddard's design revolutionary wasn't just the fuel, it was the control. Solid rockets of his era burned uncontrollably once ignited, like giant fireworks. But his liquid fuel system allowed precise throttling, even mid-flight. By mixing gasoline and liquid oxygen in a combustion chamber, then directing the exhaust through a nozzle, he unlocked the ability to adjust thrust on demand, a principle now fundamental to landing boosters vertically or steering spacecraft through atmospheric re-entry. When Elon Musk's Falcon 9 hovers above a drone ship before touchdown, it's executing maneuvers Goddard first sketched in his 1914 patent. The parallels between Goddard's notebooks and SpaceX factories are eerie. His designs included turbopumps to force fuel into the combustion chamber, identical to the Merlin engines powering Falcon rockets. He envisioned staged combustion cycles decades before Russia's RD-180 engines perfected them. Even his concept of regenerative cooling, where fuel flows through channels around the nozzle to prevent melting, mirrors the systems keeping Starship's Raptor engines from vaporizing during launch. Goddard faced more than skepticism, he endured outright hostility. After his 1920 paper, A Method of Reaching Extreme Altitudes, suggested rockets could reach the moon, the New York Times editorial board ridiculed him for lacking the knowledge ladled out daily in high schools. The article, later retracted in 1969 as Apollo 11 headed lunarward, claimed rockets couldn't work in space because they'd have no air to push against, a misunderstanding of Newton's third law so basic it's now used to teach why reactions don't need atmosphere. Isolation became his laboratory. Retreating to the deserts of New Mexico, Goddard launched increasingly sophisticated rockets, achieving altitudes over 1.5 miles by 1935. His team pioneered gyroscopic stabilization, precursor to modern guidance systems, and even tested early versions of retractable landing legs, though he died in 1945 before seeing Sputnik or Apollo. His patents became the Rosetta Stone for post-war rocketry. Wernher von Braun's team at Peenemünde studied them closely, and NASA's original 75 employees included Goddard's former protégés. The ultimate vindication came quietly. In 2012, SpaceX engineers recovering a Falcon 9 first stage discovered something uncanny. The soot-covered engines, scorched by re-entry, bore an almost artistic resemblance to Goddard's early test models. From that wobbly cabbage patch launch to reusable rockets landing autonomously, the thread was unbroken. What began as one man's stubborn refusal to accept impossible became the blueprint for escaping Earth's grip, proof that the future often belongs to those willing to be laughed at before being proven right. John von Neumann wasn't just solving math problems in the 1940s, he was quietly designing the ultimate cosmic workforce. While most scientists focused on earthbound challenges, this Hungarian-American polymath sketched out machines capable of something extraordinary, building perfect copies of themselves from raw space materials. His concept, now called von Neumann Probes, started as a thought experiment about automation. Today, it's the backbone of serious plans to explore and exploit the galaxy without human hands. The genius of von Neumann's idea lies in its simplicity. Picture a spacecraft landing on an asteroid, not just to study it, but to use it. Equipped with advanced robotics and AI, the probe would mine local metals, refine them into parts, then assemble identical replicas. Each new probe would fan out to other asteroids, repeating the process exponentially. Within centuries, a single seed probe could spawn millions, creating a self-sustaining network stretching across star systems. No need for factories on Earth or risky crewed missions, just machines that multiply like bacteria, turning dead rocks into cosmic surveyors. Right now, this isn't science fiction. NASA Asteroid Redirect mission tested early versions of space mining tech, while private companies like Planetary Resources, now defunct, and Astroforge are actively developing asteroid extraction methods. The missing piece, full autonomy. Modern robots still struggle with complex tasks like fault repair or creative problem solving in unpredictable environments. But advances in machine learning, especially neural nets that can adapt on the fly, are closing the gap. Imagine a future where swarms of these probes transform the asteroid belt into a solar-powered factory, churning out telescopes, solar panels, or even fuel depots for human explorers. Here's where von Neumann's vision gets even wilder. Some theorists propose berserker probes, hypothetical alien machines that might already exist, silently replicating across the galaxy. If even one extraterrestrial civilization launched such probes billions of years ago, their descendants could be everywhere by now. That chilling possibility fuels projects like SETI's search for artificial signals, or astronomers scanning for unusual metallic objects in our solar system. It also raises ethical questions. Should we build something that, once unleashed, could outlast humanity itself? The practical hurdles are daunting. A self-replicating probe would need universal constructors' robotic arms capable of building anything, including copies of themselves. It would require atomic-scale fabrication to turn asteroid ore into precision circuitry, and it must withstand cosmic rays, micrometeorites, and the ravages of deep time. Yet breakthroughs like 3D printing in microgravity and AI-driven material science suggest these aren't deal-breakers, just engineering puzzles waiting to be solved. What makes von Neumann's idea endure isn't just its audacity, but its inevitability. The galaxy is simply too big for flesh and blood explorers to map alone. Sending fragile humans to every interesting moon or exoplanet would take millennia, but a fleet of self-replicating scouts, they could catalog every world in the Milky Way within 500,000 years, a blink in cosmic terms. That's why scientists like Freeman Dyson and institutions like the British Interplanetary Society keep refining the math, calculating how fast such probes might spread, or how to program them to avoid unintended ecological havoc. The irony is delicious. Von Neumann, best known for shaping computer architecture and nuclear physics, might ultimately be remembered for something even grander, giving humanity the blueprint to become a galactic species. As we stand on the brink of mastering nanotechnology and artificial general intelligence, his century-old sketches look less like speculation and more like an operations manual for the future. The probes he imagined may one day float in the clouds of Venus or tunnel through Europa's ice, their designs traceable back to a mathematician's napkin doodles. And that's the power of an idea whose time hasn't come yet. Hermann Oberth sat hunched over his desk in 1923, scribbling equations that defied common sense. While most scientists assumed space travel would require brute force rockets burning endless fuel, this Romanian-German physicist saw a hidden cheat code written into the cosmos itself: gravity assists. His calculations revealed something astonishing. A spacecraft could steal a fraction of a planet's orbital energy, using it as a free boost without firing a single thruster. At the time, it sounded like alchemy. Today, it's the secret behind humanity's farthest journeys. The magic lies in celestial mechanics. Picture a spacecraft approaching Jupiter from behind, like a surfer catching a wave. As the planet's gravity pulls the probe into its well, Jupiter's massive momentum transfers a tiny fraction of its speed to the smaller object. When the spacecraft exits the gravitational tug of war, it's flung forward at velocities no rocket could achieve alone. Oberth proved this wasn't just possible, it was inevitable, governed by the same Newtonian laws that keep planets in orbit. His papers even predicted the optimal angles for these cosmic bank shots, calculating how to maximize the kick from each encounter. Fast forward to 1977, when NASA Voyager probes turned theory into reality. Voyager 2 didn't just visit Jupiter. It used the gas giant's gravity like a trampoline, bouncing outward to Saturn, then Uranus, then Neptune in what scientists called the Grand Tour. Without Olbers' math, that 12-year odyssey would have required decades more travel time or impossible amounts of fuel. Even more impressive, the tiny Pioneer 10 and 11 probes, launched with primitive 70s tech, used Jupiter's gravity to reach escape velocity from the solar system, proving a spacecraft weighing less than a compact car could outrun the Sun's grip entirely. Modern missions have refined the art to near perfection. When the Cassini probe needed to orbit Saturn, it didn't blast straight there. Instead, it performed a dizzying series of gravity assists, 2 from Venus, 1 from Earth, and finally a Jupiter slingshot, like a cosmic pinball machine. The European Space Agency's Rosetta Comet Chaser used 4 planetary flybys to match speeds with a speeding ice ball. Even New Horizons, humanity's fastest ever spacecraft at launch, got an extra push from Jupiter to shave 3 years off its Pluto arrival time. The real beauty of Olbers' discovery, it scales infinitely. The Parker Solar Probe uses Venus's gravity not to speed up, but to slow down, edging closer to the Sun with each pass. Future interstellar probes might harness the entire solar system's planets in sequence, like a relay race where each world hands off momentum to the next. Some theorists even speculate about galactic slingshots, using binary star systems or black holes as ultra-powerful accelerators for journeys between stars. What Olbers couldn't have anticipated was how his calculations would transform deep space navigation into a kind of orbital ballet. Mission planners now speak of delta-V budgets and pork-chop plots, mapping out gravity-assist trajectories with the precision of symphony conductors. The math has gotten so refined that engineers can time Earth flybys to within meters, using our planet's rotation like a booster rocket. When NASA's Juno spacecraft arrived at Jupiter in 2016, its intricate dance of 37 orbits relied entirely on gravity assists, a fuel-saving maneuver that extended its mission for years. The lesson here transcends physics. Olbers saw opportunities where others saw obstacles, recognizing that the universe itself offers free rides to those who understand its rhythms. His insight reminds us that sometimes the most powerful propulsion systems aren't built in factories, they're hidden in plain sight, waiting for someone to decipher the gravity wells we once feared. Every time a probe whips past a distant world, gathering speed from its motion, it's not just exploring space, it's proving that the best way forward might be to let the cosmos give you a push. Miguel Alcubierre was watching Star Trek in the 1990s when an idea struck him. What if warp speed wasn't just fiction? The Mexican physicist scribbled equations late into the night, bending Einstein's own rules to sketch a theoretical engine that could stretch spacetime itself. His breakthrough wasn't about moving faster than light. It was about cheating the universe's speed limit by making space move around the ship. The concept seemed ripped from science fiction, yet it emerged from cold, hard math. Today, NASA EagleWorks lab tests scaled-down versions of his theory, proving that even the wildest dreams might have roots in reality. The Alcubierre drive works like this. Imagine standing on a moving walkway at the airport. Your feet aren't propelling you forward, the ground beneath you is. Now replace the walkway with spacetime. By compressing space in front of a spacecraft and expanding it behind, the ship would surf a self-created wave, never breaking light speed locally, but arriving at destinations faster than light could travel through normal space. The math checks out. Einstein's equations allow for such curvature, but the catch is staggering. Powering this warp bubble would require negative energy, a substance that defies classical physics. Or so we thought. Recent quantum experiments hint at possibilities. The Casimir effect, where two metal plates in a vacuum inexplicably attract due to quantum fluctuations, suggests negative energy densities might exist in nature. If harnessed, even microscopically, it could provide the exotic matter Alcuibero's equations demand. NASA physicist Harold White's redesign of the warp bubble in 2012 reduced the energy requirements from Jupiter-sized masses to something potentially achievable, sparking renewed interest. Private initiatives like Limitless Space Institute now fund warp theory research, while labs explore metamaterials that mimic space-time distortions in tabletop experiments. The implications are dizzying. A functioning warp drive could reach Alpha Centauri in weeks, not millennia. It would sidestep relativity's time dilation, meaning astronauts wouldn't return to an Earth centuries older. But the hurdles are cosmic. Stabilizing a warp bubble is like balancing a soap film in a hurricane. Any imperfection could vaporize the ship. Then there's the warp shockwave problem. Arriving at a destination might unleash enough energy to sterilize planets. What makes Alcuibero's idea revolutionary isn't just the technology, it's the mindset. He dared to treat sci-fi as a blueprint, proving that imagination guided by rigor can reveal hidden doors in the universe's rulebook. Every time a physicist tweaks his equations or a lab measures quantum vacuum effects, they're inching toward a future where engage warp drive isn't just a TV command, it's the prelude to humanity's greatest journey. Nikolai Kardashev sat in a Soviet observatory in 1964, pondering a question that would redefine our search for alien life. How would an advanced civilization announce its presence across the cosmos? His answer came not in biology or language, but in energy. The Kardashev scale, a simple three-tier ranking system, proposed that civilizations could be classified by how they harness power. A Type 1 masters its home planet's energy, think global fusion reactors or solar grids. Type 2 commands its entire star, perhaps with structures like Dyson spheres. Type 3, it reigns over a galaxy, channeling the output of billions of suns. What began as a thought experiment now guides our hunt for extraterrestrial intelligence, turning distant starlight into potential billboards for alien engineering. The brilliance of Kardashev's framework lies in its universality. Energy use leaves traces, heat signatures, light patterns, radiation leaks. By searching for anomalies in these cosmic fingerprints, astronomers can scan the universe for signs of intelligence without needing to decode messages. Take Tabby's star, discovered in 2015. This bizarre flickering sun dimmed unpredictably by up to 22%. Sparking theories of an alien megastructure partially blocking its light. While dust clouds likely explain the phenomenon, the excitement around it proved Kardashev's point: unusual energy patterns are our best clues. Modern SETI has embraced this approach with tools Kardashev couldn't imagine. The James Webb Space Telescope's infrared eyes can detect waste heat from hypothetical Dyson spheres, gigantic energy collectors encircling stars. Projects like Breakthrough Listen analyze radio waves not just for deliberate signals, but for the accidental byproducts of massive engineering. Even our own planet's rising infrared signature, a side effect of industrialization, shows how Kardashev's types might be detectable across interstellar distances. But the scale isn't just about finding aliens, it's a mirror for humanity's future. Currently, we're a Type 0 civilization, still drawing most energy from dead plants and fission. Yet the roadmaps to Type 1 exist. Fusion reactors replicating the sun's power, orbital solar farms beaming energy to Earth, even geothermal taps into the planet's core, all are plausible within centuries. The leap to Type 2 seems more daunting until you consider projects like the Laser Solar Power Satellite, which could one day wirelessly transmit star energy across a solar system. Kardashev's most haunting insight was the scale's implied timeline. Given the Milky Way's age, any surviving Type 3 civilization should have colonized every viable star by now. Their absence, known as the Fermi Paradox, suggests either such societies self-destruct before reaching that stage, or they're so advanced we can't recognize their signatures. Some theorists propose even higher types, Type 4 controlling universal energy, or Type 5 manipulating multiple dimensions. What makes the scale endure is its adaptability. Originally based on radio emissions, it now incorporates quantum energy harvesting and dark matter theories. When astronomers spot a galaxy with missing infrared radiation, as if something's absorbed all its waste heat, they're applying Kardashev's logic to the grandest canvas. Whether we're alone or not, his scale remains the yardstick by which we measure our cosmic ambitions, reminding us that every watt we generate is a step toward joining the universe's great conversation. Georges Louis Lesage stood in his Geneva study in 1748, convinced he'd cracked gravity's code. His theory, tiny, invisible particles he called ultramundane corpuscles, constantly rained down from all directions, pushing objects together. Why don't we feel this cosmic hailstorm? Because larger bodies shield each other, blocking more particles between them than on their outer sides, creating a net inward force. To Lesage, this wasn't just math, it was the hidden hand behind apples falling and planets orbiting. The scientific establishment scoffed. They were right to. His push gravity violated energy laws, and the required particle speed would have vaporized matter. Yet buried in this dead-end theory were seeds of quantum weirdness we're still harvesting today. Take the cosmic microwave background radiation, the afterglow of the Big Bang. When astronomers discovered it in 1965, they found something Lesage would have loved. The universe is filled with invisible particles hitting everything. They're not pushing objects together, but their omnipresence mirrors his intuition about an active vacuum. Even more strikingly, quantum field theory describes space as seething with virtual particles popping in and out of existence, exerting measurable forces like the Casimir effect. Lesage's corpuscles were off by a mile, but his core idea that empty space isn't empty was eerily prescient. Then there's dark matter. Modern cosmology suggests invisible particles permeate galaxies, their gravity shaping cosmic structure. While these weakly interacting massive particles pull rather than push, they share a key trait with Lesage's vision: unseen constituents driving visible phenomena. His insistence that gravity might be an emergent effect, a byproduct of deeper mechanics, finds echoes in theories like entropic gravity, where spacetime's behavior stems from microscopic degrees of freedom. Lesage's greatest legacy might be methodological. By daring to explain gravity through mechanisms rather than accepting action at a distance as Newton did, he pioneered a mindset that still guides physics. When researchers at CERN smash protons together, or when theorists model holographic universes, they're following his playbook, probing the why beneath the equations. Push gravity failed, but its spirit that nature hides her secrets in layers propels every quest for a theory of everything. The lesson here isn't just about wrong ideas leading somewhere useful. It's about how science progresses through productive mistakes. For every Einstein revolutionizing physics, there are dozens of Lesage's thinkers whose errors illuminate the path forward. Their theories act as intellectual scaffolding, necessary for construction, even if dismantled later. That's why historians cherish flawed models like phlogiston or the luminiferous ether. They weren't dead ends, they were bridges to deeper understanding, proving that in science, being wrong the right way can be just as vital as being right. Galileo Galilei pointed his handcrafted spyglass toward Jupiter in 1610, and with that simple act shattered humanity's cosmic worldview. What he saw wasn't just distant pinpricks of light. Those four little stars dancing around the gas giant were moons, clear proof that not everything revolved around Earth. His crude telescope, barely stronger than modern binoculars, revealed a universe far stranger and more dynamic than Aristotle's perfect celestial spheres. Yet hidden in its flawed lenses was the DNA of every observatory from Hubble to James Webb. The parallels between Galileo's starry messenger and today's space telescopes are more than poetic. Both represent technological leaps that redefined our place in the cosmos. His device, cobbled together from spectacle lenses and a lead tube, magnified objects just 20 times, enough to spot lunar craters but hopelessly blurry by today's standards. Yet that imperfect instrument birthed observational astronomy, proving tools could extend human senses beyond evolutionary limits. Fast forward 4 centuries, and the James Webb Space Telescope's 21-foot golden mirror collects infrared light from galaxies so distant their light has traveled 13 billion years. Both instruments share the same core purpose: to see what was previously unseeable. What's astonishing isn't just the technological gulf between them, it's how Galileo's struggles mirror modern challenges. His early lenses distorted images with chromatic aberration, bending different colors of light at varying angles. Today's engineers battle similar distortions, not from glass imperfections but from space-time itself. Webb's infrared vision peers through cosmic dust, much as Galileo's telescope pierced Earth's atmospheric haze to reveal Jupiter's moons. Both required meticulous calibration. Galileo hand-ground his lenses over months, while Webb's 18 hexagonal mirrors underwent weeks of nanometer-precise alignment in space. The true legacy of Galileo's telescope lies in its democratizing power. Before 1610, astronomy was largely theoretical, dominated by philosophers interpreting ancient texts. His published sketches of lunar mountains and Medicean stars, as he named Jupiter's moons, turned celestial observation into a public endeavor. Similarly, Webb's first images weren't hoarded by academics. They flooded social media, igniting global awe. This tradition of shared discovery binds the two eras, proving that revolutionary tools lose meaning unless they transform collective understanding. Yet for all their similarities, one difference stands stark. Galileo worked alone, defending his findings against Inquisition charges of heresy. Modern telescopes like Webb represent the opposite extreme: international collaborations involving thousands, with mirrors polished by robots and data analyzed by AI. That shift from solitary genius to networked science mirrors humanity's growing recognition that cosmic truths are too vast for any one mind to hold. Galileo couldn't have imagined galaxies beyond the Milky Way, let alone instruments sensitive enough to analyze exoplanet atmospheres. But his willingness to trust the evidence over dogma set a precedent we still follow. Every time Webb detects water vapor on a distant world or Hubble captures a dying star's final moments, they're fulfilling the promise of that first, trembling glimpse at Jupiter's moons, proof that the universe will always surprise those brave enough to look. Arthur Eddington faced a room of skeptical physicists in 1920 and dropped a bombshell. He claimed stars weren't simply burning, they were transforming elements in their cores. The idea seemed ludicrous. How could atoms fuse under such unimaginable pressures and temperatures? Yet this British astrophysicist stared at the equations and saw what others couldn't: hydrogen nuclei crashing together to form helium, unleashing the energy that makes stars shine. His paper, The Internal Constitution of the Stars, didn't just solve an astronomical puzzle, it laid the foundation for humanity's most elusive energy dream. At the time, even basic nuclear physics was in its infancy. protons had only been discovered 8 years earlier, and quantum mechanics was still a controversial upstart. Eddington's calculations showed something radical. If just 5% of a star's hydrogen fused, it could glow for billions of years. That matched observations perfectly, but without a known mechanism for nuclear fusion, his peers dismissed it as hand-waving. The breakthrough came in 1938 when Hans Bethe worked out the proton-proton chain reaction, proving hydrogen could indeed fuse at stellar cores. Suddenly, Eddington's wild speculation became the cornerstone of astrophysics. Fast forward to today, and that same process powers every sunrise, but here's where Eddington's vision gets truly revolutionary. We're now close to replicating stellar fusion here on Earth. Projects like ITER in France and Spark in Massachusetts use donut-shaped tokamaks to contain superheated plasma with magnetic fields, mimicking conditions inside stars. Recent milestones are staggering. In 2021, the National Ignition Facility in California achieved a burning plasma state, where fusion reactions generated more energy than the fuel absorbed. Though we're still years from a working power plant, the principal Eddington championed that fusing light atoms could unlock limitless energy is no longer theory. It's engineering. The implications are cosmic. Fusion offers what fossil fuels never could: energy millions of times denser than coal, without carbon emissions or long-lived radioactive waste. A single gallon of seawater contains enough deuterium to match 300 gallons of gasoline's energy potential. Unlike solar or wind, fusion plants could run continuously, unaffected by weather. Even the fuel is democratically distributed. Every nation with access to water has fusion fuel. Eddington foresaw none of these practicalities, but his insight into stellar engines made them conceivable. What makes this story profound isn't just the scientific validation, it's the timeline. Eddington died in 1944, 14 years before the first controlled fusion experiment, and 80 years before we'd achieved net energy gain. Like so many visionaries, he planted trees whose shade he'd never sit under. When engineers at ITER finally flipped the switch on their first full power run, they'll be completing a century-old thought experiment that began with a man scribbling at his Cambridge desk, daring to imagine what makes stars burn. And that's the beauty of theoretical science. Today's impossible calculation might be tomorrow's power grid. Walter Hohmann sketched his cosmic highways in 1925 with nothing but pencil and paper. No computers, no space agencies, just pure celestial geometry. While most engineers of his era focused on making rockets reach the sky, this German architect turned his gaze farther out, solving a puzzle no one else had tackled. What's the most efficient way to sail between planets? His answer, now called the Hohmann transfer orbit, wasn't just elegant, it became the foundation of interplanetary travel, saving missions from Mercury to Pluto billions in fuel costs. Here's the brilliance of his solution. Picture Earth and Mars as two runners on a circular track, with Earth on the inside lane moving faster. To throw a ball from Earth to Mars, you wouldn't aim directly at where Mars is now, you'd aim for where it will be. Hohmann calculated the perfect arc, an elliptical path where a spacecraft uses just 2 engine burns, one to leave Earth's orbit and another to match Mars' speed upon arrival. The math revealed this wasn't just one option among many. It was the minimum energy route, requiring less propellant than any alternative. The numbers are staggering. A direct shot to Mars might take 6 months but guzzle fuel. A Hohmann transfer takes 6 to 11 months but uses up to 60% less propellant. That difference isn't just about cost, it's about feasibility. Every extra pound of fuel means less room for scientific instruments or life support. When NASA Viking landers touched down on Mars in 1976, when the Curiosity rover began its Red Planet trek in 2012, even when SpaceX plans its future crewed missions, they're all riding Hohmann's nearly century-old calculations to save precious resources. But Hohmann's genius wasn't just in the trajectory, it was in his foresight. His book, The Attainability of Celestial Bodies, didn't just outline transfers to Mars and Venus. He mapped routes to Jupiter's moons, speculated about asteroid mining, and even theorized gravitational slingshots decades before they were used. All this from a man who worked as a city architect by day, scribbling orbital mechanics in his spare time. When colleagues dismissed his work as fantasy, he quietly refined it, proving that the solar system's highways were written in equations long before we had engines powerful enough to travel them. The real test came with NASA Mariner missions in the 1960s. Engineers initially planned more complex routes, but when the math was crunched, Hohmann's transfers kept winning. Mariner 4's historic Mars flyby in 1965, a textbook Hohmann orbit, Pioneer Venus in 1978, same principle. Even modern missions like the UAE's Hope probe use slight variations called bi-elliptic transfers that owe their DNA to Hohmann's original work. What makes this story unforgettable is the contrast between its simplicity and impact. Hohmann didn't have quantum computers or AI, just Newton's laws and endless patience. Yet his pencil-drawn ellipses now guide spacecraft through the solar system with pinpoint precision. Every time a mission control room erupts in cheers at a successful planetary insertion, they're standing on the shoulders of an architect who saw the solar system not as a collection of isolated worlds, but as a carefully balanced clockwork, one where energy, not speed, holds the key to unlocking the cosmos. Arthur C. Clarke sat in a British radio magazine office in 1945, sketching what colleagues dismissed as pulp fantasy towers tall enough to reach space. But the sci-fi author saw further. His radical idea, not towers at all, but extraterrestrial relays parked 22,000 miles above Earth, moving in perfect sync with the planet's rotation. To most, this was just another wild tale from the man who'd later write 2001, A Space Odyssey. Yet buried in his article, Extraterrestrial Relays was the blueprint for every communication satellite now circling the globe. Clarke's genius lay in the math. He realized that at this precise altitude, now called the Clarke Belt, a satellite's orbital period matches Earth's 24-hour rotation. From the ground, it would appear frozen in the sky, allowing fixed antennae to maintain uninterrupted contact. No need for complex tracking systems or intermittent signals. Just a celestial switchboard hovering eternally over one spot. His calculations were so precise that when SYNCOM-3 became the first geostationary satellite in 1964, it slotted into place exactly as he'd predicted 19 years earlier. The impact is almost impossible to overstate. Before Clarke, intercontinental calls relied on undersea cables with delays and static. Television broadcasts couldn't cross oceans. His vision transformed the planet into a networked village. Today, over 400 geostationary satellites form an invisible grid, enabling everything from live global news feeds to GPS backups. When you stream a World Cup match from another continent or video call someone halfway around the world, you're essentially using Clarke's 1945 thought experiment as a utility. What's often forgotten is how close we came to ignoring him. Early space pioneers like Wernher von Braun initially focused on low Earth orbit for human missions. It took a young NASA engineer named Harold Rosen to champion Clarke's idea in the 1960s, battling skeptics who argued geostationary satellites would be too distant for reliable signals. Rosen's team proved them wrong by building SYNCOM with transistor technology Clarke couldn't have imagined, demonstrating that sometimes the future needs both dreamers and tinkerers to take flight. The real poetry of Clarke's orbit lies in its duality. It's a region where physics and fiction converged, where a writer's doodles became infrastructure. Modern satellites now handle darker tasks he never foresaw, like missile tracking or space surveillance, but their civilian applications remain pure Clarke. Weather monitoring, disaster relief communications, even broadcasting his own sci-fi adaptations globally, all flow through the orbital belt he first charted on paper. Perhaps the ultimate tribute came from the man himself. When Intelsat's early bird satellite launched in 1965, Clarke appeared on live TV beside a monitor showing its position. As the dot settled into the predicted slot, he grinned and said simply, "This is the end of the era of communications." He was right. The age of delay had ended, and the age of instant connection had dawned, all because one storyteller dared to treat orbital mechanics as a canvas for possibility. Ptolemy leaned over his scrolls in 2nd century Alexandria, convinced he'd mapped the heavens perfectly. His geocentric model, with Earth at the center and planets looping in intricate epicycles, small circles upon larger circles, was a masterpiece of precision. The math worked beautifully, predicting planetary motions with surprising accuracy for its time. There was just one problem: it was completely wrong. The universe didn't revolve around Earth, and planets didn't pirouette in cosmic ballets. Yet hidden in Ptolemy's flawed system was a computational approach so powerful it would echo through millennia, resurfacing in the unlikeliest of places: modern artificial intelligence. The genius of Ptolemy's method wasn't in its cosmology, but in its iterative problem-solving. Faced with planets that occasionally reversed course in the night sky, a phenomenon called retrograde motion, he didn't discard his model. Instead, he layered adjustments, adding epicycle upon epicycle until predictions matched observations. This tweaking process, known as curve fitting, is eerily similar to how today's machine learning algorithms train. When an AI analyzes thousands of cat photos to learn their features, it's essentially adding digital epicycles, refining its internal model until it can reliably recognize whiskers and tails. Both systems prioritize predictive accuracy over fundamental truth, sacrificing elegance for results. Here's where it gets fascinating. Ptolemy's epicycles weren't just mathematical kludges. They were early examples of Fourier analysis, a technique that breaks complex patterns into simpler waves. 19th century mathematicians would formalize this approach, showing any repeating curve can be approximated by summing enough circular motions. Sound familiar? It's the principle behind JPEG compression, audio synthesis, and even the AI that generates your playlist recommendations. Ptolemy stumbled onto a universal computational tool 2,000 years before computers existed. Modern data scientists face a Ptolemaic dilemma daily. When training neural networks, they often encounter overfitting, where a model memorizes training data with absurdly complex parameters but fails with new inputs. It's the digital equivalent of Ptolemy adding endless epicycles to explain Mars's wobbles. The solution: regularization techniques that punish unnecessary complexity, forcing models to find simpler patterns. In a twist of historical irony, today's AI researchers are relearning the same lesson Ptolemy never could. A model that's too perfectly tuned to past data may be useless for predicting the future. The real legacy of Ptolemy's epicycles lies in their philosophical audacity. He trusted the math over dogma, even when it led him astray. That willingness to iterate, to tweak, test, and refine is the beating heart of modern data science. When Netflix adjusts its recommendation algorithms or meteorologists fine-tune storm models, they're following his playbook. Not every epicycle leads to truth, but each brings us closer to patterns hidden in the noise. And that's the ultimate lesson. Sometimes the wrong answers point toward the right methods, bridging the gap between ancient stargazers and the coders shaping our digital skies. Edward Barnard peered through the telescope at Yerkes Observatory in 1916, tracking a faint red dot streaking across the sky 10 times faster than any known star. This cosmic speedster, later named Barnard's star, wasn't just another point of light, it was a revelation. At just 6 light-years away, our stellar neighbor revealed something groundbreaking. Stars aren't fixed landmarks, but travelers with their own motions and mysteries. What Barnard couldn't have guessed was how his discovery would ignite a century-long hunt for planets beyond our solar system, transforming his unassuming star into a testing ground for exoplanet science. The secret lay in that rapid motion. Barnard's star's close proximity and high velocity made it the perfect laboratory for detecting subtle wobbles, the telltale sign of orbiting planets tugging on their host star. For decades, astronomers dreamed of spotting these gravitational fingerprints, but the technology lagged behind the theory. Then came the Kepler Space Telescope in 2009, armed with precision light sensors capable of spotting a star dimming by just 1 part in 10,000 as a planet crossed its face. Suddenly, the galaxy teemed with worlds, hot Jupiters, super-Earths, even planets orbiting binary stars. Kepler's treasure trove of over 2,600 confirmed exoplanets proved what Barnard's work had hinted: planets aren't the exception, but the rule. Enter TESS, the Transiting Exoplanet Survey satellite, launched in 2018. Where Kepler stared at a fixed patch of sky, TESS scans 85% of the heavens, hunting for planets around the brightest nearby stars, stars just like Barnard's. In 2018, decades of wobble measurements finally paid off when astronomers announced Barnard's star B, a frozen super-Earth 3 times our planet's mass, orbiting every 233 days. The irony is delicious. The star that taught us how stars move also hosted one of the nearest known exoplanets, found using methods Barnard himself pioneered. What ties these eras together isn't just technology, it's the power of patience. Barnard spent years painstakingly photographing the same star fields to track minute movements. Modern planet hunters continue that tradition, with TESS monitoring each star for weeks and teams like the Pale Red Dot campaign collecting decades of radial velocity data. The tools have evolved from glass plates to CCD sensors, but the core challenge remains: distinguishing planetary signals from stellar activity, a puzzle Barnard's star exemplifies with its notorious flare activity. The legacy of that 1916 observation now extends beyond science. Barnard's star features in everything from Asimov's Foundation novels to debates about interstellar probes, with Breakthrough Starshot considering it a potential first destination. Its story embodies astronomy's grand narrative: how meticulous study of the familiar can unveil the extraordinary. Every time TESS spots a new world or James Webb analyzes an exoplanet atmosphere, they're walking the path Barnard's fast-moving star first illuminated: that the universe rewards those who watch closely, measure carefully, and dare to ask what dances unseen in the dark. Georges Lemaitre stood before the world's top physicists in 1927, a Belgian priest with an outrageous claim: the universe had a birthday. His cosmic egg theory proposed everything we see, from galaxies to stardust, once burst forth from an unimaginably dense point. To the scientific elite, this sounded less like physics and more like Genesis rewritten with equations. Even Einstein initially dismissed it, quipping, "Your math is correct, but your physics is abominable." What they couldn't see was that Lemaitre's calculations held the key to a cosmic revolution waiting to unfold. The irony was delicious. Lemaitre wasn't some medieval scholar mixing scripture with starlight. He held a PhD from MIT, studied under Arthur Eddington, and understood relativity as deeply as anyone. His insight came from combining Einstein's equations with redshift data from distant galaxies. While others saw static celestial islands, Lemaitre spotted a pattern. The farther away a galaxy was, the faster it seemed to be receding. His math showed this wasn't random motion. Space itself was stretching, carrying galaxies apart like raisins in rising dough. Extrapolate backward far enough, and the entire observable universe would crunch into what he poetically called the primeval atom. Hubble gets the glory for confirming cosmic expansion in 1929, but Lemaitre had predicted it 2 years earlier. Using Slipher's redshift measurements and Friedmann's solutions to Einstein's equations, he calculated the rate of expansion, a figure now called the Hubble constant. When Hubble's observations matched Lemaitre's predictions, the scientific world couldn't ignore the priest's fireworks theory any longer. Yet even then, resistance lingered. Fred Hoyle famously coined Big Bang as a mocking term during a 1949 radio debate, unaware the name would stick as the theory triumphed. The real turning point came in 1965 when Penzias and Wilson accidentally detected the cosmic microwave background, the afterglow of Lemaitre's primordial explosion. That faint static hissing from every direction was the smoking gun, radiation cooled over billions of years from a searing initial state. Suddenly, the cosmic egg wasn't metaphor, it was measurable reality. Modern satellites like COBE and Planck would later map this radiation's minute fluctuations, revealing the seeds of galaxy formation in temperature variations smaller than 1 part in 100,000. Lemaitre's legacy isn't just about changing how we see the universe's birth. It reshaped our understanding of time itself. Before him, even Einstein imagined an eternal, unchanging cosmos. The idea that space had a history, that atoms in our bodies trace back to a singular fiery beginning, was philosophically staggering. It meant the night sky wasn't just a place but a story, one with chapters written in receding starlight and elemental fingerprints. What makes Lemaitre's journey unforgettable is its duality. A man of faith who never let theology dictate his equations, he represents science at its purest, following evidence wherever it leads, even when it sounds like revelation. His theory faced decades of skepticism not because it was weak, but because it was too radical for its time. Today, when astronomers peer back to within a fraction of a second of the Big Bang or simulate quantum fluctuations blossoming into galaxy clusters, they're completing a quest that began with a priest's unshakable curiosity. The universe, it turns out, doesn't care who unlocks its secrets, only that someone dares to ask. Enrico Fermi leaned back in his chair during a lunch break at Los Alamos in 1950, staring at a cartoon of aliens unloading trash cans from flying saucers. The room buzzed with talk of interstellar travel probabilities when he dropped his now famous question, "But where is everybody?" In that moment, the Fermi Paradox was born, a haunting riddle that shaped our search for cosmic neighbors ever since. If the universe is so vast and ancient, why does it feel so empty? The numbers tell a story that makes the silence even stranger. Our Milky Way alone contains over 100 billion stars, many older than the Sun by billions of years. Even if just 1% of those stars hosted life, and 1% of those civilizations developed technology, the galaxy should be teeming with activity. Where are the Dyson spheres harnessing stellar energy, the interstellar probes passing through our solar system, the radio signals leaking from distant cities? This discrepancy between expectation and observation, between cosmic abundance and eerie quiet, fuels SETI work to this day. Modern solutions to Fermi's paradox range from sobering to surreal. Some theorists propose great filters, evolutionary roadblocks that prevent most life from reaching interstellar stages. Maybe microbial life is common, but intelligent life inevitably destroys itself through war or ecological collapse. Others suggest advanced civilizations might transcend physical forms, uploading consciousness into quantum matrices or black hole computers, leaving no traces we'd recognize. There's even the unsettling zoo hypothesis that aliens observe us like wildlife, enforcing a galactic prime directive. Yet the search continues, armed with tools Fermi couldn't have imagined. SETI Allen Telescope Array scans thousands of stars simultaneously for artificial signals, while Breakthrough Listen analyzes petabytes of radio data using machine learning. The recent discovery of technosignatures, potential markers of alien technology like industrial pollution in exoplanet atmospheres, adds new dimensions to the hunt. Even our own leaky TV and radio broadcasts, radiating into space for decades, serve as a case study for what to listen for. The paradox's deepest impact might be philosophical. Fermi's question forces us to confront whether intelligence is a fluke or a cosmic inevitability. Each silent night sky observation carries twin possibilities, that we're either the universe's firstborn or its last survivors. Both answers are equally humbling. As we scan the stars with increasingly sensitive instruments, we're not just searching for aliens, we're seeking our own place in a story whose ending remains unwritten. Zeno of Elea posed a riddle 2,500 years ago that still makes physicists pause. How can an arrow ever reach its target if, at every instant, it's motionless in space? His paradox sliced motion into infinite frozen moments, suggesting movement was an illusion. Philosophers wrestled with it for centuries, but the real surprise came when quantum mechanics resurrected Zeno's puzzle in the atomic realm. Suddenly, those ancient thought experiments weren't just brain teasers, they were blueprints for controlling reality at its smallest scales. The quantum version flips Zeno's logic on its head. Imagine an unstable atom poised to decay. In the quantum world, observation itself alters outcomes, a principle called the measurement effect. If you bombard that atom with frequent measurements, something bizarre happens, the decay stalls. It's as if the universe, caught under the microscope, freezes in place. Physicists call this the quantum Zeno effect, where constant observation essentially traps a system in its initial state. The arrow isn't just frozen, it's kept frozen by the act of watching. This isn't just theory. In 1989, researchers at the National Institute of Standards and Technology demonstrated the effect with beryllium ions. By repeatedly measuring the ion's energy states with laser pulses, they suppressed quantum transitions that would have occurred naturally. Later experiments with ultra-cold atoms and superconducting circuits confirmed it. Observation isn't passive. It's a tool that can literally slow down time for quantum systems. Now here's where it gets practical. Quantum computing harnesses this effect to stabilize qubits, the fragile building blocks of quantum information. By strategically kicking qubits with measurements, engineers reduce errors caused by unwanted jumps. It's like using Zeno's paradox as a cosmic pause button, buying precious microseconds to perform calculations. The same principle even shows up in medicine. PET scanners rely on radioactive decay timing, and understanding quantum jumps improves their precision. What's poetic is how history loops back on itself. Zeno imagined motion as a series of still frames to argue against change. Today, we exploit that very idea to manipulate matter. His paradox, born from pre-Socratic debates, now helps debug quantum algorithms and could one day extend the lifetime of quantum batteries. The arrow finally reaches its target, not by denying Zeno's logic, but by embracing it as a feature of the universe's deepest workings. Sometimes the oldest questions unlock the newest frontiers. Leonardo da Vinci dipped his quill into ink one evening in 1510, sketching not just the moon's luminous face but the ghostly glow of its darkened side, a phenomenon we now call earthshine. While others dismissed it as celestial magic, Leonardo saw a mirror. His notes, buried between anatomical studies and flying machine designs, proposed something radical. The moon's night side catches light reflected from our own planet, like a dim echo of sunlight bouncing between worlds. At the time, this was heresy. The Church taught that celestial bodies were perfect, unchanging spheres, not rough surfaces trading light like common objects. Yet da Vinci's artistic eye for light and shadow had uncovered a truth that wouldn't be confirmed for centuries. What's astonishing isn't just the accuracy of his insight, it's how he got there. Without telescopes or spectrometers, Leonardo relied on painterly intuition. He noticed that sunlight striking Earth must illuminate the moon just as moonlight brightens terrestrial nights. His sketches even accounted for variations in Earthshine's intensity, suggesting clouds and oceans altered our planet's reflectivity. Modern photometers aboard satellites like NAS and Discover now measure this exact effect, quantifying how Earth's albedo fluctuates with weather patterns, proving da Vinci's qualitative hunch with digital precision. The real magic lies in how Earthshine bridges art and science. When Apollo astronauts photographed Earthrise over the lunar horizon, they captured the same glow Leonardo described, our planet casting its blue radiance onto the moon's ashen plains. Today's researchers use Earthshine's subtle changes to study climate change, since shifts in cloud cover or ice melt alter Earth's reflectivity. The Lunar Reconnaissance Orbiter maps these variations, turning the moon into a giant mirror reflecting planetary health. But da Vinci's legacy goes deeper. His moon studies reveal a mind untethered from dogma. Where contemporaries saw divine perfection, he saw textured terrain, correctly deducing mountains and valleys from the jagged terminator line between light and shadow. Centuries before Galileo's telescope, he even speculated about a thin atmosphere scattering light around the lunar limb, a phenomenon astronauts would witness firsthand during solar eclipses. The lesson here isn't just about lunar science, it's about perspective. Da Vinci treated the cosmos as a grand studio where light obeyed universal rules, whether illuminating a portrait or a planet. His Earthshine epiphany reminds us that breakthroughs often come from cross-pollination when artists think like scientists and scientists observe like artists. Every time a modern researcher analyzes Earthshine data or a photographer captures the moon's ghostly crescent, they're walking the path a polymath painter traced by candlelight, proving once again that truth, like moonlight, often reaches us by unexpected reflections. Johann Bode stared at his notebook in 1772, convinced the solar system hid a numerical secret. His formula, later dubbed Bode's law, wasn't physics as we know it, just a curious pattern. Start with 0, add 4, then double each subsequent number, 0.4, 0.7, 1.0, 1.6, and so on. Multiply these by 10, and voila, they roughly matched planetary distances from the Sun in astronomical units. Mercury at 0.4, Venus at 0.7, Earth at 1.0. Even the gap at 2.8 hinted at something undiscovered. When Herschel spotted Uranus in 1781, its orbit fit Bode's prediction of 19.60 almost perfectly. For a moment, it seemed the cosmos played by simple arithmetic rules. Then the cracks appeared. Neptune's position defied the sequence entirely, and Pluto, later demoted to dwarf planet, shattered any remaining illusion. Bode's law wasn't a law at all, just a coincidence with a few lucky hits. Yet here's the twist: that failed pattern now fuels how we hunt planets light years away. Modern astronomers use similar statistical approaches to predict where exoplanets might lurk in distant systems, not because the universe obeys tidy math, but because patterns, even imperfect ones, help narrow the search. Consider the Kepler Space Telescope's treasure trove of exoplanets. Before staring at random stars, scientists prioritized those with stable, long-lived environments, stars resembling our Sun, orbiting in so-called Goldilocks zones. This targeted approach, reminiscent of Bode's educated guesses, led to discoveries like Kepler 452b, a rocky world orbiting its star at nearly the same distance as Earth. The difference: today's models incorporate chaos theory and gravitational dynamics, acknowledging that while patterns exist, they're threads in a far messier cosmic tapestry. Bode's real legacy isn't his formula, it's the mindset. His willingness to seek order in celestial chaos paved the way for tools like the Titius-Bode relation, which still helps identify plausible orbits in newly discovered exoplanet systems. When astronomers found TRAPPIST-1's 7 Earth-sized worlds in 2017, their neatly spaced orbits sparked debates about resonances and migration patterns. The numbers didn't match Bode's sequence, but the underlying question was identical: what hidden rhythms might govern planetary spacing? The irony is delicious. A discredited 18th century rule now inspires 21st century science because it embodies a deeper truth: sometimes wrong ideas lead to right methods. Bode's failed law taught us that the universe rewards those who look for connections, even if the connections themselves evolve. Every time a machine learning algorithm flags a star's subtle wobble as a potential planet hunter's target, it's echoing Bode's audacity to find sense in the stars, one imperfect pattern at a time. Hypatia stood in the great library of Alexandria around the year 400, her fingers tracing the worn edges of star charts as whispers of rebellion swirled through the city streets. While most remember her brutal death at the hands of a mob, few know how profoundly this mathematician and astronomer shaped our understanding of the cosmos, or how systematically her contributions were erased. Her annotated editions of Ptolemy's Almagest refined celestial models that guided navigators for centuries. Her designs for astrolabes, ingenious devices that mapped star positions, became the GPS of the ancient world. Yet for over a millennium, her name nearly vanished from history, surviving only in fragments and footnotes. What makes Hypatia's story so pivotal isn't just the tragedy of her silencing, it's the pattern it reveals. For every famous male astronomer whose theories we celebrate, there's a Hypatia whose work was dismissed, a Wang Zhenyi in Qing Dynasty China calculating lunar eclipses in secret, or a Caroline Herschel cataloging comets only to see her brother William credited. The erasure wasn't accidental. When Hypatia's library burned, when her student records were destroyed, when her inventions were attributed to male colleagues, it sent a message: women's minds didn't belong among the stars. Yet here's the paradox: even as their names were scrubbed from textbooks, these women's ideas persisted. Hypatia's refinements to Ptolemy's planetary models indirectly influenced Kepler. Her hydraulic device for measuring liquid densities inspired medieval Arab scientists like Alhazen. Like cosmic background radiation, their contributions hum beneath the surface of modern science, detectable only to those who know where to listen. The backlash against women in astronomy took many forms. When Maria Mitchell discovered a comet in 1847, newspapers marveled that a mere woman could achieve such a feat. When Henrietta Swan Leavitt decoded the relationship between Cepheid variable stars' brightness and their distance, the key to measuring the universe's scale, her Harvard supervisors barred her from pursuing her own research, relegating her to a computer role analyzing male astronomers' data. Yet without Leavitt's discovery, Hubble couldn't have proven galaxies existed beyond the Milky Way. Today, the tide is turning, in part because we're finally recognizing how much was lost. Projects like the Hypatia Catalog, a database of women-led astronomical research, and the Asteroid Hunter app, where volunteers honor female scientists by naming discoveries after them, actively rewrite the narrative. At institutions like the Lick Observatory, historians pore over glass plate archives to recover hidden figures like Williamina Fleming, who classified over 10,000 stars while labeled as a maid. The most profound shift isn't just about justice, it's about scientific progress itself. Studies show diverse teams solve complex problems faster. When Jocelyn Bell Burnell detected pulsars in 1967, her male advisor won the Nobel Prize while she was overlooked. Yet her later advocacy for inclusive research environments directly enabled discoveries like the Event Horizon Telescope's black hole image, achieved by a team spanning 40 countries. The lesson is clear: when we silence half the species, we have our potential for discovery. Hypatia's legacy lives every time a young girl peers through a telescope at a school astronomy night, or when missions like NASA Lucy, named after the fossilized human ancestor discovered by another overlooked woman, Mary Leakey, launched to explore Trojan asteroids. The shadows of erased women still stretch across time, but now they point not to what was lost, but to what's possible when we finally let all minds navigate the stars. From Kepler's celestial choreography to Alcuibero's warp drives, the history of space exploration isn't just a timeline of technology, it's a testament to the power of stubborn imagination. These visionaries didn't merely predict the future, they invented it from whole cloth, armed with nothing but parchment and conviction. Consider the irony. The same equations scribbled in margins by dismissed dreamers now guide billion-dollar missions, their authors' names etched on spacecraft and craters. The lesson here isn't just about scientific progress, it's about how we define what's possible. Look around our cosmic toolkit today, and you'll find echoes of their audacity everywhere. Ion thrusters humming on deep space probes, that's Tsiolkovsky's handwriting in the static. The James Webb Space Telescope parked perfectly at Lagrange point 2. Euler and Lagrange's celestial math made it possible. Even the search for alien megastructures owes its methodology to Kardashev's seemingly whimsical energy scale. What unites these breakthroughs isn't just their brilliance, it's the decades, sometimes centuries, it took for the world to catch up. This pattern begs a thrilling question. What modern impossibilities are currently gathering dust in some lab notebook or RZIV preprint? Maybe it's quantum vacuum propulsion, harvesting energy from spacetime itself, or self-replicating nanobots transforming asteroids into cosmic waste stations. Perhaps it's the young grad student sketching antimatter, harvesting techniques between coffee breaks, unaware their doodles might fuel the first starships. History suggests the wildest ideas often age into inevitabilities. If we're bold enough to preserve and revisit them, the true value of these forgotten theories isn't just in their accuracy, it's in their mindset. Each pioneer shared a willingness to be spectacularly wrong in pursuit of being spectacularly right. Kepler wrestled with nested platonic solids before landing on ellipses. Goddard's early rockets looked like inverted fireworks before evolving into Falcon boosters. Progress isn't a straight line from a to be, it's a chaotic scribble of trial, error, and occasional brilliance. That's why we must protect today's fringe ideas, not despite their strangeness, but because of it. So here's our challenge as cosmic citizens: nurture the heretics. The next time you hear a theory that sounds like science fiction, be it wormhole engineering or dark energy manipulation, ask not whether it's immediately practical, but what doors it might unlock in a century. After all, the dreamers of the past didn't build the future by conforming to consensus. They built it by daring to be ridiculous, then letting time vindicate their vision. Who's to say the blueprint for interstellar travel isn't already hiding in plain sight, waiting for its moment? The universe reveals its secrets to those stubborn enough to keep asking, and imaginative enough to recognize the answer when it arrives. Now it's your turn. Which modern idea seems impossible today but inevitable tomorrow? Drop your predictions below, and let's keep the conversation soaring. For more journeys through science's forgotten frontiers, hit subscribe. The next breakthrough might be lurking just beyond the horizon.